Hello, everyone. Today we're going to be going over dynamic equilibrium, which is your 30s. We're going to be giving you a lot of background information to start off with, and hopefully by the end of this presentation, everything will make sense. So we need a few terms to go over at this point in time. The first one's called dynamic. What does that mean? It means constant change. Earlier in this unit, we did an aquarium where we're taking one bucket and dumping it into an aquarium and a different container, dumping it into a different aquarium. That dynamic part was that movement of water back and forth. So there was constant change going on. And what does equilibrium mean? You can think of it as balance, kind of like equilibrium on a seesaw. That'd be where both people are at the same height. So dynamic equilibrium is established once the rate of the forward reaction and the rate of the reverse reaction are equal to each other. So what are we talking about? We're talking about reactants over on the left-hand side, making some products, and those products breaking apart, going back into reactants at the same rate. That's what we would mean by dynamic equilibrium. So there's constant motion between the products and reactants in dynamic equilibrium. Dynamic equilibrium is sometimes called chemical equilibrium, and sometimes it's just flat out called equilibrium. Again, feel free to pause the video at any point in time today. If you were in class, we'd be watching this video. We're going to skip this part. You can write down Le Chatelier's principle. That's also on your cover if you need to write it down from your cover. This is something that needs to be memorized at some point in time. And feel free to pause the video to get a chance to write this down. But Le Chatelier's principle is stated as, if a system at equilibrium is subjected to a stress, the reaction will shift to lessen the effect of that stress. So when we apply a stress, it's going to shift to lessen that stress. That's the key point with Le Chatelier's principle. Again, pause the video as needed as we're going today. In industry, Le Chatelier's principle is used to get the most amount of product, the quickest, and the cheapest. So this skill that we're teaching you in this unit, using Le Chatelier's principle, is one of those major components that you will use if you are a chemist out in industry. So we're going to be talking about a lot of shift today. You can go home and talk about all the shift that happens in chemistry. They probably won't understand, but shift happens. So there's 4 types of stress that can occur in an equilibrium system. The first one is we can change the temperature. This triangle sign means change in. So we can change the temperature. We also need to realize that in the problems that we're working with, a change in temperature can also be called a change in energy. You could also call that a change in kilojoules, maybe even kilocalories in some problems. So we're talking about all the same thing. A change in pressure. Now, pressure of a gas is how often particles are hitting the sides of the container. So that's what we define as pressure, how often particles are touching or hitting the insides of a container. And that would be dealing with gases. We could also change the volume, which would be the same thing as changing the pressure. We could also add a reactant or product. We could also remove a reactant or product. So those are different types of stress. I know it says 4 types. These 2 are basically meaning changing the amount of product or reactant. So that's why we have 5 things written up there, but really we're asking for 4 things. So not of all what is removed will be what by a shift. So Le Chatelier's principle, you're going to stress out the reaction, and it's going to shift to lessen said stress. So if I remove something, it's going to try to replace it by a shift. And if I add something, it's going to try to remove that. So whatever my stress is, the reaction is going to shift to lessen that stress, to reduce that stress. Again, a lot of this information doesn't make a lot of sense right now, but hopefully by the end of this video, all of the pieces will fall in place. So here's a chemical system. We have reactant A. This would be an ion. We have reactant B. This would be an ion. And these two ions come together to make a compound. And as you can see, compound AB is red in color. And the two ions A and B, they are colorless. So that is what we're going to deal with initially. So ions A and B are colorless, and when they come together, they make a red compound, which is called AB. So A and B are colorless. We can see that right there. AB is a compound. It is red in color. Imagine the following system at equilibrium. Colorless ions can link up to form colored compound. The red compound can split apart into colorless ions. All three substances are present in the solution at equilibrium. So if we look at this, this would be a beaker right here, and all of that is occurring inside the beaker. So we have some of the ions that are colorless, and then we have some of the red compound. All of that is there. If you can imagine this, this would be like if you were making some Kool-Aid and you put a little bit of the Kool-Aid packet in it, you would expect the whole thing to turn a certain color. So this is probably a pale red color right now. The redness does not change because the red making equals the red losing rate. So if these two break apart, then these two might form together to make a red compound. So it's constantly happening in dynamic equilibrium. If a red one breaks apart, then two colorless ones come together and make some more red. That's dynamic equilibrium. So the reaction is as follows. The real reaction is as follows. So we have some iron, some Fe3, and it's colorless. So we got some Fe3 right here, and it's colorless. We got some SCN, and it's colorless. But when they come together, they make iron 3-thiocyanate, which is red in color. So this is an actual chemical reaction that we could be doing. So at the atomic level, again, we have some colorless that are in there. We have some red molecules that are in there. And that'd be at the atomic level. And at the macroscopic level, it just looks like a beaker that's red. So we have all of these things in there, and it just looks like it's a beaker that's red. So here we go with number 8. If we add some Fe3 positive, and equilibrium is achieved, again, by shifting how? So if I increase the amount of Fe3 positive, that is my stress. The reaction is going to shift to reduce that stress. The only way to get rid of Fe3 positive is for it to react with SCN and make some iron 3-thiocyanate. That's the only way that you can reduce the amount of iron ions that are there. So if I add some Fe3 positive, it's going to shift to get rid of it and make more of the FeSCN. So it's going to shift to the right. So I'm going to erase all that. So again, if I increase this element, this iron 3 ions, it's going to shift to get rid of it. The only way it can shift to get rid of it is to make more of the product. And these two would have to react together to make more of this product. So now let's go to the next question. What happens to the amount of iron? Well, if I'm adding Fe3 positive, the amount of Fe3 positive is going to go up. So the reaction is going to shift to try to get rid of it, but it cannot get rid of all of it. So if you add something, its amount will increase. What happens to the amount of SCN? Well, when I add some Fe3 positive ions, it's going to react with the SCN ions to make some iron 3 thiocyanate. So what's going to happen to the SCN? Its amount is going to go down. It's going to decrease. And what happens to the amount of FeSCN or iron 3 thiocyanate? It is going to go up. Because again, the FeSCN is reacting. So these two are reacting together, and they're going to make more of that. So it's going to go up. So let's just recap all of that. It's not really a question, but let's just recap it all. If I increase this, this amount's going to go down because these two are going to react with each other. If those two are reacting with each other, they're going to make more of this, so this is going to go up. So now we're going to shift a little bit, and we're going to come back to it at the bottom part of this page. So in this first chemical reaction, we have energy needing to get put into a chemical reaction to get it to occur. This would be like a chemical ice pack. Energy goes in, it takes energy from its environment, so it's something that gets colder when the chemical reaction occurs. So when energy is found over as a reactant, that's called an endothermic reaction, and that is because energy is consumed or used to make the chemical reaction occur. In this next one, in number 10, the energy is over here as a product. So when this chemical reaction occurs, energy will be given off. This would be like the hand warmers, the chemical hand warmers that you can buy from Fleet Farm. You open up the package and they start to get warm. This is called an exothermic reaction, and that is because energy is released or given off. In number 11, it says if you add energy or raise the temperature of the reaction will shift to do what to the energy? So if I am increasing energy, the reaction is going to shift to use up that energy. So if I'm increasing the energy, the reaction is going to shift to use up that energy. And it's going to end up shifting to the left towards the reactant side. If you remove energy or lower the temperature, which way will it shift? So now I'm going to be removing some energy. The reaction is going to shift to try to replace that energy. So the reaction is going to shift this way to try to replace that energy that I am removing. So it will shift to the product side or to the right to try to produce some of that energy that I removed. So again, whatever stress you place on a chemical reaction, the reaction is going to shift to minimize or reduce the stress. So if you add something, it's going to shift to replace it. If you remove something, it's going to shift to make more of it. All right, so here's a chemical system. We have hydrogen gas, nitrogen gas, and it makes ammonia. Which way will the reaction shift if there's an increase in pressure? Well, pressure is all about gas molecules, and it's really the only thing that it affects is gas molecules. So we need to count up how many gas molecules we have. So we have 3 gas molecules here. We have 1 gas molecule here. So on this side, we have 4 gas molecules. On this side, we have 2 gas molecules. So which way will the reaction shift if there's an increase in pressure? So what we have to understand is this is my container here. I know I'm awesome at drawing. What has more pressure? A container that has 4 gas molecules in it, or a container that's got 2 gas molecules in it. And pressure is defined as how often the gas molecules hit the side of the container. I would say 4 gas molecules right here are hitting the sides of the container more often than these 2 gas molecules are. So in other words, with 4 gas molecules, there's a greater pressure. With 2 gas molecules, there's a lower pressure. So let's read question 13 again. It says, which way will the reaction shift if there's an increase in pressure? If you increase the pressure on the system, it's going to shift to the side that's got less pressure, and that would be the 2 gas molecules. So it's going to shift to the right to the 2 gas molecules. Pressure does not affect what? Well, if it only affects gases, it does not affect solids, liquids, or aqueous solutions. So when the stress is pressure, we only have to look at the gases. The only stress that will change K is a change in energy. This was found out through various experiments. It's kind of hard for our brains to grasp it, but through a bunch of experiments, it was found out the only thing that will ever change K is a change in energy. Changes in pressure occur due to changes in volume, which change the molarity of a gas and will not change K. Again, scientists did experiments to find out that adding and removing solids and liquids did not shift chemical reactions. So you just have to take our word for it that the only thing that will change K is a change in energy. So here are some problems on the back side of your sheet. It says this reaction is occurring in a beaker. The stress is that more Cl2 is pumped into the beaker. Draw an arrow to state which way the reaction will shift to reduce the stress. When more Cl2 is added, it will cause an increase in molarity, decrease in molarity, or no change in molarity for each of the items. Circle your answer. So my stress is increasing chlorine. If I increase chlorine, it's going to try to reduce the amount of chlorine. The only way it can reduce it is if these things react with each other and make these things over here. So the reaction will shift that direction to make more of the products to get rid of some of the Cl2. So that is the way that it will shift. Let's start off with the stress is more Cl2 is pumped in. So if this is going up, it's going to increase. Remember, when you add something, the net effect is it will go up. H2O is a liquid. So since it's a liquid, there's going to be no change in molarity. We learned that in our 15s experiment. Molarity does not change for liquids and solids. If you add more moles, they take up more liters, and the molarity stays the same. If these things are reacting with each other to make these items over here, the energy is going to be used. So some energy is going to be consumed in this problem. Some water molecules are going to be consumed as well, but the molarity of the water molecules will not change. So if we are shifting this way to make more products, we would expect the hydrochloric acid to go up. We would expect the oxygen to go up. So I'll erase that, and I'll give you a couple more pointers. Most of the time, after you figure out the shift, the things at the tip will increase, and the things at the butt, this is my butt of my arrow right there, will decrease. That would be these things. But there are exceptions. This water, no change. We're adding Cl2, so it's going to increase. This one does decrease. So the general rule, things at the tip go up, things at the butt go down, but like we just saw in this problem, there are 2 exceptions to that rule. Let's go and do another problem. So in this one, the stress is some oxygen gas is removed. So this is going down. So the reaction is going to shift to try to make more of it. To make more of it, the reaction would have to shift this way. For us to make more HCl and more O2, these items have to react with each other. Again, the Cl2 will react with the water, so some water molecules will be consumed in this reaction, and some energy will be consumed to make the reaction go this way to make more HCl and O2. So Cl2 will go down. H2O will be no change because, again, it's a liquid. The molarity will not change. So as we use up some moles, we're also using up some liters, and the molarity stays the same. We would be using up some of the energy, and we would increase the amount of HCl. Now, the O2, the stress is O2 is removed. So the O2 concentration is going to go down. So again, things at the tip of the arrow tend to go up, but here's my exception. It does not. Things at the butt of the arrow tend to go down. And that is true all except for this one. Let's try another one. Why don't you try this one on your own and see how you do? Pause the video. The stress is pressure is increased. So pressure deals with gas molecules. So I have two gas molecules there. I have one O2 on this side, so I have one gas molecule. Again, here's my awesome containers. Whoa, that really went wrong. So this side has one gas molecule in it. This one has two gas molecules in it. Pressure is defined as how often gas molecules hit the sides of the container. With two gas molecules, they should be hitting the sides of the container more often than one gas molecule. So there's a higher pressure with two gas molecules and a lower pressure with one gas molecule. So again, the stress is pressure is increased. So the reaction is going to shift this way to one gas molecule because there's less pressure there. So these items will react to make these products. So what happens to Cl2? Well, it's going to decrease because some of it's going to be used up. Some water molecules are going to be used up as well, but again, their molarity will not change, so it's a no change. Some energy is treated just like an element off the periodic table. It will be used. You need energy to go along with these. And what will it make? It will make some more HCl. It will make some more O2. And those will go up. So in this case, things at the tip of the arrow did go up, did go up. Things at the butt of the arrow did go down. No change, did go down. This reaction is occurring in a beaker. The stress is the beaker is heated. So when I heat something, that is energy. So this is a fancy way of saying the energy is going up. The only way I can remove energy, according to Chatelier's principle, if I increase the temperature, it's going to shift to reduce the temperature. If I increase the energy, it's going to shift to try to reduce the energy. So if my energy is going up, it's going to shift this way to get rid of that energy. These three things are reacting to make these two products. So let's go through this. I am increasing the energy. That's my stress. It says the beaker's heated. So my energy does, in fact, go up. My molarity of my water will not go down, but we will use up some water molecules. We will use up some of the Cl2 molecules. We go over to the other side. HCl, hydrochloric acid, and oxygen gas, both of those will go up. Again, things at the tip of the arrow tend to go up, and they both do. Things at the butt of the arrow tend to go down, and they do, except for energy was being increased in this problem, so it can't go down, and there's a no change with that one. So the problems that we just did can be summed up on the data table. So if you look at the next page, we put it all into a data table. Instead of what we did in circling, you're going to use arrows for increase, decrease, shifting to the right, shifting to the left, or NC for no change. Those are things that you're going to be using on the next page. So again, words are going to be replaced with arrows. Remember, K is products over reactants, and K values can only change when there is a temperature, energy, or kilojoule or kilocalorie change. These all really are meaning the exact same thing. They are all a change in energy. They're just given to you in many forms. And why do we give it to you in many forms? So when you go off to college, you don't freak out when they start using kilojoules instead of saying temperature or energy. So that's why we are giving that to you. So 30.2 is your homework. Go ahead, give that a shot. We will talk to you later.